So, okay, we are just waiting for the audience to join in, and till then, let me give a brief some introduction. It's quite a matter of coincidence that I have my friend Reis also with me, and we're as of now having this conducting this session from IIC, Indian Institute of Science. We're basically located in Centenary Guest House. I had thought I'll conduct it from some other location, but it so happened that Reis just joined and he just arrived in Bangalore, and we thought of having it together. So just waiting for more people to join in. I hope the voice and other things are coming clear. Okay, guys, let's get started. My name is Rukhsan, and I am professionally I am a theoretical physicist. I am working in the area of I got my PhD in quantum condensed matter physics, especially working in the area of strongly correlated electron systems. So presently, I am working on it's more towards quantum computation and machine learning and AI, artificial intelligence. That's what my current interests are. That's what my current focus is. So, and also what I did is that because there's a lot of activity on the industry side when you come to the machine learning and artificial intelligence. It has recently picked up. There's a lot of after research in deep learning, as you would have heard of AlphaGo and other achievements which were done from neural network side. So there was a lot of activity from the industry side, and as of now there are many new fields which have emerged, like as people call them artificial intelligence. We have already heard. So new field is data science. So data science is kind of a new emerging field which is interdisciplinary because it involves computer science, statistics, and some maths also. But there's a lot of activity on that side. And while I was doing my PhD, I got interested in machine learning, and then there is interface between machine learning and some theoretical physics. So I'm exploring that connection. That's what I am currently working on. So I'll come back to my research later on. So let me tell you what's going to be our format as of now for the today's session. So what we will do is that first of all, I will talk about theoretical physics in general and what are the avenues possible for the young students and the researchers also. And then I'll shift more towards my own specialization, which is quantum condensed matter physics. I'll say why is it an important area of research, especially for the new people who want to join in. And little later, I will talk about some details of my own work, and then we will also have an occasion to talk about this important career opportunity, which is nowadays becoming, I think, a lot of people are considering it, which is the transition to the industry, because industry is also opening its gates to research. So I'm sure many of you would have heard of, like, Google is doing fantastic work. They have a Google Brain project. Similarly, on artificial intelligence, machine learning, there are lots of projects being run by Google. Similarly, Microsoft and similarly Facebook. And incidentally, as of now in my current work, one of the libraries which I'm doing, which I'm using, is basically came from the research from Facebook. So they have developed some of the libraries for the machine learning, and I'm using one of them. So I'll come to that again. And later on we will have, in the end, we will have some announcement to make, and talking about some opportunities for the young students and researchers. Okay, so theoretical physics, as many of us know, that it's a huge umbrella of many interesting fields of research, starting from quantum gravity, high energy physics, particle nuclear physics, then coming back to so we have classical mechanics. There we have developments in nonlinear dynamics. We have complex systems, statistical physics, which in itself is a huge world. There are lots of applications, and the theory side, or mathematical physics side. And then there is a quantum condensed matter physics side, or in condensed matter also we have something called a hardcore condensed matter physics, which studies the solidus and condensed, or some fluidus. But then we have a soft condensed matter physics as well, which studies more of biological systems. So there are lots of important research areas. Theoretical physics is a huge umbrella, and all of them are very, very important. All of them are equally interesting, equally fascinating for any of researchers. But what happens is that as the history of the subject evolves, there are some more important areas, and there are some which do not become as important. Let me give a concrete example of high TC superconductivity. If you go back to 1980s, high TC superconductivity was a big news, and all of the people were joining in, and because they believe that they thought maybe they can make a breakthrough in high TC superconductivity. But the breakthrough has not come even now. I mean, after so many after decades of research, it has not happened. So now what happens is that this high TC superconductivity goes in the backdrop. There is not much of research on that side. It's not such an active area as presently is, say, topological phases of matter, which got kick-started in 2008 when people were able to make the first topological insulator. And from then onwards, there are more new kind of from an experimental side also, new materials have been devised, new systems have been discovered. Like another important system is the Weil semi-metal, which was experimentally discovered in Princeton. Okay, and so the shift as of now, if you see, so there is always, that's what I'm saying, that there is a shift of the research interests. Some areas which we colloquially say that some of the areas are hot areas, and some of them are not so hot areas. But the ones which are not hot areas doesn't mean they are less interesting or something of that sort. It is just that we as a research community sometimes put more sustained effort in one subject or the other one, and when we have to, it becomes important from this point of view that if we have to make career choices, it will give us more benefits if we are in the right area of theoretical physics. So that, I think that's what is important. Otherwise, the whole theoretical physics, whatever area you pick up, it's always interesting, it's fascinating, it always has been, and it always remains so. Okay, so so from my point of view, some of the important areas which I think where there is a lot of activity is, definitely I can speak from condensed matter point of view. So is the main condensed matter. There are in condensed matter also we have this, as I said, a hardcore, which is called quantum condensed matter physics, which involves basically studying the physics of strongly correlated electrons, because if the electrons are not strongly correlated, physics solving those problems becomes trivial. So which are like free fermion systems which can be easily kind of studied. So while as if we have the strong correlation, the whole business becomes a different ball game. And understanding strong coupling problems is one of the most unsolved problems in whole theoretical physics. Not only in condensed matter alone, I think it becomes even more difficult in solving strong coupling problems, say in QCD, where you have actually a strong force in action, while as in case of condensed matter system, we have this electromagnetic force which plays the role of the interactions. So this is one of the important unsolved problems. We do not have as of now a full-fledged theory for solving any strong coupling problem in whatever field it is. Okay, so there is a need for development of new areas, new methodologies to tackle such problems. And similarly on the once again in condensed matter system, so there are new developments which have from experimental side point of view mainly, or this is called cold atom physics. So cold atom physics is like what we do in any condensed matter system, in any solid system, quantum system. So you try to simulate the same thing in terms of lattice of the lasers. You have these optical lattices, and you basically try to simulate the same physics. For example, I have a problem of understanding what happens to electrons when there's a strong interaction. What I would like to do is that basically simulate the same physics on an optical lattice. And then why is it important? Because there's more control on optical lattices, which are basically lattices made up of laser light, rather than in terms of the actual solids. In the actual solids, there is not much control, and that's why we cannot do much with, we cannot tune many things, we cannot explore the whole phase parameter space over there. So that's why there is on the experimental side, there is a lot of interest on cold atom physics, which is a very emerging area. So that is one area where new researchers, especially the ones who have interest in experiment also, they can join. And it also brings back old atomic physics, because it's a physics of the rubidium or other atoms. Those are the atoms which are being involved here also. And that's one important emerging area, cold atom physics, in the hard condensed matter side. Similarly, from the soft condensed matter also, what the plan is that, because condensed matter physics, it's different in this sense, because the principles of condensed matter physics are not something which are just restricted to physical systems alone. So this is one of the important things about condensed matter, that the principles are very much statistical, I would say quantum statistical principles, which can be simultaneously applied not only to physical systems but to biological systems as well. And that's precisely what's happening, that people are taking these principles or even methodologies which from the condensed matter physics side and applying to other biological systems. Say we want to study the colonies of the bacteria and see what's happening over there, the way they do the collective motion, and it becomes important understanding bacteria. And it's wonderful for a physicist to take his methodology, whatever methodology and conceptual framework he has understood, and basically apply it to biological systems, and where it will make an immediate impact in healthcare if we understand bacteria better, how do they interact and how do they survive. So that way we can have a correspondingly a very robust drug design system. Okay, so these are kind of two main maybe two different directions within the condensed matter itself if one wants to explore. But just a couple of comments in condensed matter system is that there are questions many people ask is like friends ask me, how is quantum field theory being applied over there? So my immediate answer to that is yes, why not? Because these are quantum systems. How else are you going to understand them? I would tell them that it's not just quantum field theory. It's not a quantum field theory of a Dirac fermion coupled to electromagnetic field that we are going to applying here. Rather, it's another kind of a field theory which is called a statistical field theory, that you have to develop a quantum field theory for a full collectivity of the electrons. It's one step ahead, one step more complicated, one step more complex, because it's, as I said, it's you have to write down your quantum field theory, your Lagrangian, for a full quantum system. Okay, and that's why I call it. That's why people call it statistical field theory. And simultaneously, you will have, it's not a zero temperature quantum field theory; it's a finite temperature quantum field theory. So all the calculations which you will like to do are all at a non-zero temperature. Okay, and all the correlation functions you calculate, or all of them are, because we are not always interested in zero temperature correlation functions. So that way, all of the stuff which we have available from the field theory side, all those things are being applied, because in fact some of them got developed in condensed matter only. Because take an example of conformal field theory. Conformal field theory, the first example of application of conformal field theory was to critical phenomena. People were trying to understand second order phase transitions And then they realize that at the point of the phase transition, there is this critical point, and at that particular point, there is enhancement of the symmetry. It becomes actually not only scale invariance, rather it becomes full-fledged conformal symmetry group, and people have to write down similar field theories, which are conformal field theories, and then they were applied to some other areas of research as well. Similarly, there are other things also which are like as topology. Topology has a very important interface to condensed matter physics. In fact, as of now, there's a full-fledged research program, research field which has emerged, which is called the topological phases of matter. And the one definition of for those who are interested from field theory side, so for them an immediate definition is a topological phase of matter is a phase of matter whose description can be given in terms of a topological quantum field theory. One important example of topological quantum field theory is the Chern-Simon gauge field theory. And the Chern-Simon gauge field theory is basically the field theory which was written down for quantum Hall systems. In the two dimension, the quantum Hall physics is effectively it is described by Chern-Simon gauge field theory, and as many of us know that it's a topological quantum field theory. Okay, the Hamiltonian doesn't play so much of a role. It's the non-local Wilson loop operators. For those of you who understand, it's the Wilson loop operators who act as observables in the theory. So all of that stuff, whatever you have studied, it is the right kind of condensed matter is the right kind of playground for all those areas, concepts, and the technology which you have learned from the mathematical machinery you would have learned. And if you are very mathematically minded also, then I would say condensed matter is for you, because condensed matter physics as of now is the only area of research, to the best of my knowledge, where the most abstract mathematical methods, like as the category theory, is being applied. Category theory is playing more and more important role in condensed matter physics. And category theory, as many of you know, is highly abstract, is one of the most abstract areas of mathematics. And it's quite interesting to note that on the one side, this immensely abstract mathematics finds concrete applications in a field, research field, which deals with the concrete stuff, with quantum stuff, concrete systems, solids, and that's why it's quite interesting to note that. So that's for condensed matter system and the research opportunities and what kind of work you will be doing, and what kind of projects, what kind of possibilities of pursuing a career in condensed matter system. So my suggestion from a personal experience is that it is one of the most exciting areas which we have as of now in theoretical physics. I would say from every point of view, you look at from the application point of view, there's an immediate application. For example, in my own research, what I'm doing is working on these topological phases of matter, understanding them better, developing new theories, because we do not have full-fledged theories for such systems. But simultaneously, it has an immediate interface to something called topological quantum computing. Okay, so what I'm doing is it can be always translated. So whenever we build these topological quantum computers, they are going to be built on these topological quantum systems. So it has an immediate interface. You can always shift. You always basically switch back and forth between understanding something from topological quantum computation and bringing it back to the topological phases of matter. So that's an immediate interface which at least I personally like, that I'm working on something which is going to build a technology and which will bring an immense revolution, not only in 1, 2, 3 countries, but rather it will change the whole course of the human history, like as the computers did some years, a few decades ago. It's something of that is being built as of now. I would say even more revolutionary than that. And you as a theoretical physicist are being part of that revolution. You are part of building that quantum computation revolution. So to me, it looks very exciting, and I'm sure many of you will find it also exciting to do it research that way. But simultaneously, for those of you who would like to say, okay, I'm not too much into applications, I want more of theoretical stuff, I would once again say that condensed matter is again that area, because as I mentioned already, so you take any mathematical method, any mathematical concept, and you just find out, you will find an immediate application. You will see it is there in condensed matter. If somebody would have already thought about it in condensed matter side, as I already mentioned, these category theories or the higher category theories, people have already understood how they are being basically brought in as a theoretical structure into condensed matter physics systems. Okay, the concrete example is when you look at these quantum Hall systems. two-dimensional electrons. Just you apply a magnetic field in 2 dimensions, it becomes a quantum Hall fluid. First of all, if there are no interactions, then it's an integer quantum Hall fluid. But if there are interactions, it becomes fractional quantum Hall fluid. But when you try to understand them, what's going on over there, so what you see over there are not electrons. So in that quantum Hall fluid, it's not made up of electrons anymore. What has happened is that the electrons have coupled to the magnetic field, and they have given rise to another kind of a particle, which is an anion. And this anion is neither a fermion nor a boson. And so you cannot apply your standard quantum field theory, because standard quantum field theory is either for fermions or for bosons. So the question is, what do you do? How do you write down a quantum field theory for such a system? Okay, and that's where Frank Wilczek and many other people came in, and there is this I forgot his name. So there is another physicist who played an important role over here, because they were the people who wrote down these field theories for such systems, and they were the people who realized that in two-dimensional systems, in this quantum Hall system, the statistics is not fermionic or bosonic, rather it's anionic statistics. So nowadays these anionic statistics play a very important role, because they are the guys from which we are going to build our topological quantum computer. Okay, so that's just to give you a significance or the feel for what is going on at the research frontiers in condensed matter physics. What are people doing? This is what I'm telling you. I would say you can just read any recent paper from what's coming from the Microsoft Quantum Station, and you will just read any recent 2019 paper, and you will see these are the things they are working on. And it's pretty significant. Microsoft has realized that it's pretty significant for the whole humanity, and they just want to commercialize it. These areas, they want to commercialize this areas. They want to commercialize this field theory. They want to commercialize whole machinery, and also simultaneously maybe build the idea is to build the technology for the future. Okay, because quantum computers are on the way. They are not very far from us. They are just coming. Okay, so this is the kind of interface condensed matter has, especially the quantum condensed matter side has. Similarly, condensed matter has other sides also. Let's say you look it from a statistical point of view, you look at different phases of matter. Like as one example which comes to my mind is this glass transition. And these glass transitions have not been understood, because they do not fall under the usual phases of phase transitions. They're not standard phase transitions, classical phase transitions. So from that point of view, what condensed matter is, on a broad question which we ask in condensed matter physics, is what are the various phases of matter? What is the organization of matter? How can matter organize itself in various different ways? And what can it give rise to? What are the different phases of matter it can give rise to? Okay, so those are the questions. And in classically, we have these classical phase transitions, which say, for example, a phase transition from no superconductivity to a superconducting phase. And similarly, you may have other magnetic phase transitions, but we have also other phase transitions, something called a quantum phase transition. And in quantum phase transition, it is the quantum fluctuation. By quantum fluctuation, I mean the fluctuation coming from the uncertainty principle, that there is non-commutation between various conjugate variables that leads to the quantum fluctuations. And it is these quantum fluctuations which drive the phase transition in many quantum systems. Okay, and once again, we do not have a full-fledged theory for that, and that's another research area. And maybe you have heard of the name of this Professor Subir Sajdev. He is an authority on that. He has written a book on the subject. But if you look through the book, it's still, there are models, there are field theories, but many of things have been understood, but it's still not complete. The story is not complete. It's still an open research area. Okay, so those were the things on the list to tell you on from a condensed matter point of view. Also, I talk about, there are definitely, I mean, I'm not saying that condensed matter, definitely it will be too much wrong to say that condensed matter physics is the only game in the market. It's in the only game in the town. It's not like that. There are even bigger questions, even more important questions which theoretical physicists are dealing with. Because if we look at our cosmos, I can say, I'll not be too wrong to say that there are two categories within which we can divide our cosmos into. One is this category of the space and time together, So this is space and time. Then rest of it is matter and radiation. If I forget about the matter for a time being, radiation time being, so we have on the one side we have space and time, and on the other side we have this matter. What condenser matter is looking at is this material matter aspect, okay? And the realization, one of the important realization is that the whole matter, whatever matter is, as we know, is fermionic. Fermions are quantum, they are supernodal. So this is one of my, I'm fond of saying this statement that matter is basically supernodal. And this is one of the important things why there is a lot of excitement, because the whole supernodal matter, this whole quantum matter, okay, we have not, it is just at the beginning of this century that humanity had the first understanding of what matter is. So we have always been living in this physical universe, matter has been always there, but it's only at the beginning, after the inception of quantum mechanics, that we had the first glimpse, humanity had the first glimpse into what matter is. And the glimpse was this thing, that matter, and it was Sommerfeld, Arnold Sommerfeld, the well-known mathematical physicist, who understood that matter is obeying a different kind of statistic. It's fermionic in nature, and he divided first to free fermion gas, and he understood many things. Fermi statistics came in, which was very, very important for understanding band theory and the semiconductors. So, but the main important theoretical area was understanding that matter is basically fermionic. And what I am trying to tell you that we are just at the beginning of understanding the supernodal nature of matter. We are not done yet. It's just the beginning. And what we have understood along the way, we have discovered transistors. We know semiconductor theory. We build transistors. We build computers. We understood superconductivity. And superconductivity is essentially quantum mechanical phenomena. It comes from this property of these electrons on the fermions. And fermions are very tricky objects. They're much, much trickier than the bosons. It's rather, from a theoretical side, it's easier to understand bosons, because bosons are our well-known friends, harmonic oscillators, and we as physicists are friends of harmonic oscillators. We know them very well. But when you come to the fermionic world, everything changes. The first change which happens is that whenever you want to describe fermions, you cannot use your well-known number systems. You cannot use real numbers. You cannot use complex numbers as well. You have to introduce something called the Grassmann numbers. So Grassmann numbers give us the description of the fermions. Neither of the other systems can do. Okay, and that's why when we deal with the fermionic objects in field theories, we use Grassmann variables. Okay, so that is just to give you a first glimpse of how trickier these objects are, how difficult it is to deal, because it's entirely new. This is a quantum world. This is something which we had not heard of. In a classical world, they teach us about vectors. They teach us vector analysis. They teach us everything about vectors. But what I'm telling you is that matter is not vectorial. It's not. It's supernodal. And what we are doing is that, and then supernodes have connections. Then they have topological properties. And what we recently realized in the last five years is we have understood the topological aspects of these fermions. Okay, we have understood that these new phase of matter. Let me do a short description of one of them. It's called a topological insulator. The guys which do not conduct, when you apply electric field to them, they do not conduct electricity. But what is happening into these topological insulators is a strange behavior, is that they do not conduct. Once again, inside the bulk, they do not conduct. But then they have conducting states at the edges of the system. Let's say if we have a three-dimensional system, on the surface of the insulator, topological insulator, there will be conducting states, but inside the bulk, it's once again the conductivity will be zero. Okay, and this property is the same thing which we call holographic property. So the quantum matter is also holographic. Okay, it has this holographic behavior, that it has one behavior in the bulk and then another behavior on the boundary. And but this bulk and behavior, there's a correspondence. It's not that what's happening on the edges or the boundary is negligent of what's happening on the bulk. There's a relation between bulk and edge, and this is that famous bulk edge correspondence. Okay, so this is just to mention you another aspect of what's happening on the topological phases of matter, that they are showing these holographic properties. Then they have connections to the topology in the sense that if you look at the conductivity, what's going on the edge states is the only way you can describe them is in terms of some methods from algebraic topology, because these guys are topological invariants. The conductance is a topological invariant over here. Okay, similarly, I want to point out another thing, just to tell you how quantum matter is behaving. how the supernodal aspects of the quantum matter are showing up, how they're exhibiting. And I will just focus on two things which I want to mention immediately. Is usually you will believe, I mean, we have been told in textbooks that there is this relativistic domain and then there is non-relativistic domain. Condensed matter in that definition follows on the non-relativistic side. Okay, everything is non-relativistic. Electrons are not following they're not moving very fast. Okay, they're on the non-relativistic, they have a non-relativistic dispersion. That is known. But what happens in these topological states of matter is something you would not have even, I mean, imagined. What's happening is that I talked about these edge states. So all the edge states are in a condensed matter system, in a quantum system, in an insulator, topological insulator. And but the equations, the way they behave, they follow not the Schrodinger equation. They are not behaving as non-relativistic electrons. They are behaving as relativistic electrons. They're behaving as Dirac electrons. Okay, so this is amazing. So what is, you may not have realized it, let me say it explicitly. What is happening is that relativity is emerging in a system which is not non-relativistic to begin with. There is no shred of relativity in a solid. There is no relativity over there. But when you take it to this topological phase, when you make it a topological insulator, what's happening on the edge? In the bulk you have the same electrons, again non-relativistic electrons, but on the edge you have these Dirac electrons. And the answer, I mean the question arises: how is this relativistic dispersion arising over here? Where are these Dirac electrons coming from? Okay, this is an important question, and this is altogether different way of understanding relativity, because in relativity we are always being told, this is a textbook, a class or a school way of understanding relativity, is that you go to higher speeds, that's why relativity becomes important. I'm telling you other way around. I'm telling you that we have an actual phase of matter, a solid, which you can go and test in a lab. You can find these Dirac dispersion playing a role. You can see in your spectrum of that solid, that Dirac cone. Okay, it's arising in a non-relativistic system, and it's on the edges. It's not the whole system. It's showing this behavior, and this is an important question in topological state of matter. And let me tell you, condensed matter systems have an answer for that. We have an answer. Where is it coming from? Okay, and then you can, I mean now, as I said, holographic connection is here. You may bring in more other things. You may bring in maybe some connection to the conformal field theory, and yes, there is, and there are more connections which we would like to understand. So I was just trying to illustrate that how bizarre, how strange, how weird is this quantum matter, and it is still just the beginning of this story. I'm hoping that it will take us I don't know how many centuries to understand the quantum matter, the full aspects of the quantum matter. Okay, so it's altogether new. As I said, in the quantum states of matter, emergent principles are at work. We have not the usual theory of Einstein's usual theory of relativity at work. We have something called the emergent theory of relativity at work in condensed matter systems. And now we have to understand it again. I mean, we have to see how is relativity emerging. What is this emergent relativity principle? Okay, so it gives us a new way for those who are interested in relativity. It's a new exercise for them, understanding that maybe relativity is not fundamental. It can arise in situations where it was not there in the beginning. So they have to look at it again. They have to revisit relativity and see whether it's fundamental or it's emergent, or if it is emergent, which it is in condensed matter systems, what are the consequences? Okay, or for gravitation and other systems. Okay, so that's another example which I am saying that why is it important? What is happening on a condensed matter side? Just to summarize, is that we have got hold of these supernodal guys, which are not vectorial objects, and we put them in interactions. They show even more bizarre behavior, and then we are understanding them. That's what quantum condensed matter system is about. Okay, and then a lot of new technologies are being built. Like one which I am very fond of is this category theory method. It's very abstract method, but it helps us to understand a lot of what's going on in the condensed matter side. Okay, and then other thing which I am, once again, this another direction which I like a lot, is that you ask the question. You see in classical computers, how was the information processing happening? So you had some magnetic systems, or you had some maybe voltage devices where you would say you have some kind of switches where you store your information as on and off way, or in a magnetic system maybe up and down way. Okay, that's how information you will store. But these quantum systems, condensed matter systems, they offer you new ways of processing the information. First of all, I would say storing the information, because magnetic systems give you a new way of storing the information. and simultaneously a new way of processing the information. So quantum systems are offering us new way of computation, which is basically called the quantum computation, that where you access these quantum properties of these systems and do quantum computation in a new way. I'll give one example on which which is my research area, is something called the topological quantum computation. For any quantum computation system, what you need is a qubit. Okay, it's a two-level system. That's what you need to begin with, and then you do the processing on that. You have quantum gates which act on the qubit, then they do the rest of the processing. But one of the system are the spins, which we know, magnetic systems, but other systems which are the superconducting systems. In the superconducting also, you can have these two-level systems, fermions. Okay, and now what I'm describing is a topological superconductor. Earlier I talked about topological insulator. Now I'm talking about topological superconductor. In a topological superconductor, what happens is, unlike what earlier we had a Dirac fermion arising on, or Dirac fermion is arising on the edge of a topological insulator. Here in topological superconductor it's not the Dirac edge, it's not the Dirac fermion, it's rather a Majorana fermion. And Majorana fermion, as we know, are the real solutions to the Dirac equation. Okay, it's very interesting. Something had happened when we go from insulators to the superconductors. We basically go from one kind of solution to the Dirac equation to another kind of solution to the Dirac equation, or we go basically from one representation, which is the Dirac representation, to the Majorana fermion representation, Majorana representation. We know, all of us know, that there are three kinds of solutions available to Dirac equation. One is Dirac, one is Weil, and one is Majorana. And in case of topological superconductors, what is arising on the edge is a Majorana fermion. It's a Majorana mode. It's just basically what's happening is that a single fermion. This is bizarre. I want to talk about it a little bit. This is quantum entanglement in action in topological superconductor. You have the one single fermion. It's not single two fermions, one on one edge and another on another edge. You have a chain of superconductor. We have a one-dimensional superconductor. And the same Majorana fermion, one single Majorana fermion, is basically being split. One edge is on one part of it, half of the fermion is at one edge, another half of the fermion is at another edge. And it is quantum entangled through the full chain. This is actual quantum entanglement in action. So that's how it is. So it's a non-local guy, which is spread throughout the full Majorana, this Kitai chain, this one-dimensional superconductor. Okay, and you cannot do anything to it. It's so robust. It's spread. It's non-local object. You cannot. It's because it is robust. If you store some information in this Majorana fermion, so it's going to be robust. That is the idea. That's what Alexei Kitai told us. That if we encode our information in these Majorana fermions, because they are non-local objects, nothing is going to take them away. So we are getting a new way of encoding the information. This is called a topological way of encoding the information. Topological. This is the beginning of the topological quantum computation, because once you store in Majorana fermions, rest will be to go ahead and apply the quantum gates to these systems. And that's another story. How do you build the quantum gates for such systems? But here I am telling you, these topological systems are providing us altogether different way of storing the information and doing a different kind of quantum computation. And this is what, just for your information, this is what Microsoft is doing. You can just Google and go to the Microsoft web page on their quantum station, which is in Santa Barbara, where I applied and didn't get it. Is so competitive. Okay, to go to that headquarters of Microsoft, and that's where it's being built, and the future of our topological quantum computation. So this was just all of this discussion in my work was about to tell you how it is only at the beginning of this century that we had a glimpse of what matter is. And I'm telling, and we know the answer, matter is fermionic and matter is supernodal. And what we are doing as of now is just exploring these aspects of the matter, of quantum matter. Now people call it topological quantum matter because they have realized that these fermions are topological essentially. Bosons are not. Bosons are like they're local guys. By topological, I mean many things, but non-local first of all. That fermions are non-local. As I just showed you one of the fermion, Majorana fermion. It is essentially, actually, you can do an experiment and see it's basically spread throughout the chain. You can do such an experiment. Okay, and that's what is going on in quantum condensed matter physics. That makes me exciting because it's altogether new field of research, which just it just started just say 56 or 80 years back, and then it's a long journey ahead. Okay, so that was about quantum condensed matter system. Now, in the end, I would like to conclude by saying that I'm also interested. There are other new directions which I mentioned in the beginning. Is something called machine learning and deep learning and artificial intelligence. People call it different names. So they are also playing a very, very important role. There are many physicists have started basically applying these machine learning in physics, different areas of physics. One of the most important example is the LHC itself. Where we cannot do, I don't think we should be able, no human, I don't know, if we all of us get together to basically look into the data which is getting produced there, we will not be able to do if we do not have these machine learning algorithms at our disposal. So they are running all the time over there with the Python code, Python simulation, Python graphical interfaces, and that's where they are helping us a lot. But that's just one example where they're being. Astrophysics is another example. Astrophysics people have developed their own Python implementation of these things, and a lot of it is being applied. And similarly, in condensed matter physics also people have started applying, and I think it must be spreading to other areas also, because as you know, we have people are from the computer science, they are talking about driverless cars, they are talking about so much of automation, they are talking about Internet of Things, IoT data, IoT sensors. So a lot of activity, a lot of things, developments have happened on the computer science side. You may also know that how nowadays neural networks are basically winning the games of chess, winning the games of Go, and they are the champions. Nowadays, humans are not the champions of these games. They are the robots who win these games better than us. They do better than us at these games. So the question is that how do we leverage, how do we take these machine learning algorithms or the tools which have been built on the machine learning side and try to understand some of the fundamental questions on theoretical physics side. So that's what I'm currently working on, and I'm very happy to tell you that in one of my recent activity, what I did is that I was applying these algorithms and getting some. The problem was something like this. Let's say I am working on a stock market situation, and my job is to predict what's going to happen to the stock market, say in coming 24 hours or say 6 hours. And I'm applying these algorithms, and typically one would like to get a very good accuracy for these predictions. And that's what happened. I applied these algorithms, I had the data, and I applied. And what was amazing to see at my group in Bangalore over here was that I was able to get, at least for some situations, an accuracy of 100%. Okay, and we were amazed. We didn't believe that it's possible, but it was. I got an accuracy of 100%. So done rightly. I mean, I think when I was doing, my other colleagues are from computer science, but I think my background from theoretical physics, from my computational background, played an important role in getting those things right. So that's another direction which we can explore. I mean, many theoretical physicists can explore that direction because we have the right kind of mathematical machinery available to us. We can use it and basically build careers on other direction also. So if any of you is interested on that side, from machine learning side, feel free to contact me on Facebook or WhatsApp. I would like to, I'll be happy to give more details or inputs on that side. And similarly, we are just one more announcement. Coming back to earlier point, because this shift from academia to industry, it's not so simple, it's not so smooth. There are people at work who charge you, and like I will take example of one organization. It's called a cheeky scientist. So cheeky scientist is one organization who are going to charge you money. They're not going to give it free, and simultaneously they will not guarantee you that the transition will happen. They will just guide you, give you resources and all that, give you access to certain materials. But simultaneously, it's not guaranteed that if you join cheeky scientist that tomorrow you will have a good job on an industry side. It's not so simple. It's not a smooth journey. So, but I think from my side, what I can do is that I can give a lot of inputs on that, some kind of a career guidance. How can we make it happen? Or if some people they don't want to go to physics directly, they just directly want to go to the machine learning stuff. I can to those students also I can now share some guidance. Okay, so that's on the machine learning side. So now also in the finally I would like to announce that for the students who are based in Kashmir, and I know, I mean, all of us know who are in theoretical physics, we know how difficult it is, this journey of basically ending up kind of a successful theory guy. It's a thorny and a very tricky, tortuous journey, because one has to build up a lot of background before one can successfully deal with any problem in theoretical physics. It's a long journey. So what we have done, and with my many good and very nice friends, have started building a platform for students in Kashmir, so that we can make their journeys to theoretical physics very smooth. So we are calling it, as of now, the name we are giving is a Kashmiri Institute of Mathematical Sciences. It's not an institute somewhere grounded as of now, but it's a platform which we are trying to bring up and running very soon. We will trying to get, capture spaces for the institute, and other things are logistic things are happening as of now. But even now we have some WhatsApp group running. Facebook help is also available. So whosoever wants to have a research career, they can get in touch with us. We will make sure that we give them all the support, make their journey smoother, and both technically also, career wise also. We have many friends who are outside the outside country also. They are more than happy to help these students, so that it should not happen that a person, a very talented guy, just for the lack of the exposure, he didn't end up realizing his dream. We want more people realize their dreams, because those people who are successful, happy inside, they are the real assets for not only for just for Kashmir, but for the whole humanity. And it is those people, I believe, will drive the future. Okay, so that's why it's very, very important for us to help these guys to realize their dreams, and have more have a big community of scientists and theoretical physicists, computer scientists, and who can drive this, who can redefine our, because we do not have a history of theoretical physics in Kashmir, so we have to write it again. I mean, first time we have to write it, and I think we're all set to write it, redesign it in such a manner that we have our own space in theoretical physics and other mathematical sciences. So I think I'll stop there. That's what, and if there are, I know there were many people who are not able to join because of many things. So what I'll do is that I'll quickly go through some of the questions and try to answer them. Yeah, okay. Anha is talking about simulation tools that I use. So earlier I was using some different tools, but mostly the language was Python. Essentially, I'm a huge fan of Python language. And I was doing Monte Carlo simulations, something called quantum Monte Carlo simulations. But as of now, what I'm doing is more on machine learning side. There are lots of machine learning, deep learning algorithms. And once again, I am more or less using Python again in my calculations. So, but I'm more than happy to talk about these details privately also, so that I can do. Yes, Anha has a very important point over here. Yeah, that's what I was referring to, low dimensional systems only when I talked about quantum Hall physics situation, which is a low dimensional system. And the modern analog, I would say the graphene. Graphene is a two-dimensional sheet, which is playing a very important role. And for those of you who are from high energy physics side, I would say graphene is basically the lab to realize all that Dirac physics. Because earlier also I mentioned that, see, graphene is a non-relativistic system. It's basically the carbon atoms in a lattice. So that's what it is, usual carbon atoms. But when you look at the way the dispersion is, the energy dispersion is, and the way electrons are behaving inside a graphene, they are behaving not as the non-relativistic electrons, rather than they are behaving as Dirac electrons. And that's why there is a lot of interest. The interest in graphene is because precisely for this reason, that electrons are behaving as Dirac electrons, and that gives rise to the ballistic transport. Okay, so there is, yes, there is a lot of interest in low dimensional quantum systems, and this I was just mentioning one. Graphene is one of them, but then people are building more different versions of graphene. I don't have the details of all of them, but I know there's a lot of interest on that side. People are working actively on that side also. And similarly, low dimensional will mean also nanowires or the nano systems. So they will also the one-dimensional superconductor which I was talking about is actually a nanowire system. It's a very small system, a small nanowire, and it is giving rise to these fermions. Another thing which I had worked with earlier in my PhD was something called Kondo effect. It takes place in the situation is the quantum dot. So you have a quantum dot, and on the quantum dot you have these charging energy. It's a small island, small dot, and on that you have charging energy, and it gives rise to something called Kondo effect. And that if you have a particular kind of a Kondo effect, it leads to the enhancement in the thermoelectric effect, thermoelectric coefficient, thermoelectric transport. So yes, there is a lot of interest. 2D systems are very important. 1D systems, essentially 2D systems, they have very peculiar and interesting behavior from technology point of view. Yeah, I think those were more or less the questions. So, but as I said, I'll be more happy if I'll be happy to answer all those questions if you have any. So, but I think more or less I'm done. That's what I wanted to talk about. Riso, namaste paraungi. Yeah, I'll end the session. Huh? Okay, yeah, I think there's one question which came. Yes, there is a question from friend Irfan Rathar. So coming, yeah, stock markets. I would not say, no, dear friend, it's not. I wouldn't say it's available to the public. Yeah, but what I was saying is that there are tools based on machine learning. There are tools, and we can make predictions about. And I can show you one way of doing the stock market predictions based on the tools which I'm using as of now. So that way it is accessible in the sense that I can show you how we can make a practical example of how we can make predictions. But then prediction of stock markets is a separate industry in financial markets. It's a separate industry. There are experts over there, but still there are basic tools which can be used, especially my point is following. My point is that nowadays people are not using conventional tools of stock market prediction, rather they're using machine learning tools and deep learning tools. Okay, and those are the ones which we know, and ideally we should be also able to do the stock market predictions. Okay, but I myself have not explored this option, though I am quite fond of this thing. I have not explored it too much. Okay, I think, okay, thank you all for joining, and offline I can take more questions or any comments, whatever you want to ask. I can take those questions offline. Thank you for joining, and take care.